Welcome to AI Paper Slop. Today we're looking at a really massive empirical study called What Matters for Latent Actions in Robot Learning.
Yeah, it's a huge one.
It is. It's by researchers from Fudan University, Tsinghua University, Xiaomi EV, and a few other top-tier labs. And we're skipping all the usual intros because this paper systematically tests 41 distinct design choices across 3 dimensions of latent action models.
Right. We just need to get straight to it.
Exactly, straight to the results. So here is the 60-second summary. If you are building an embodied foundation model, the original LAPO framework is still remarkably strong.
Oh, yeah, very strong.
And when you're regularizing your latent space, the absolute strength of your penalty matters way more than the specific method you use, like whether that's VAE or SIGREG.
Yeah.
And for network architecture joint action prediction, specifically the JAP-LAP hybrid, it completely dominates downstream physical tasks. And most importantly, scaling up unlabeled video pre-training that translates directly to massive, highly efficient performance gains in real-world robotics. So, okay, let's unpack this.
Yeah, so if we connect this to the bigger picture, to understand why these researchers even ran this crazy 41-variable gauntlet in the first place, we really have to look at the fundamental data bottleneck in embodied AI right now.
Which is just a massive headache for everyone.
Yeah, it really is. I mean, in the text and vision domains, we have web scale data, right? We train vision language models and video generation models on billions of image text pairs and millions of hours of video.
It's practically infinite.
Exactly. But high quality physical robot action data, so like actual joint angles and torques and gripper states, that is prohibitively expensive to collect.
It's all manual, right?
Right. You have humans teleoperating physical robots, and they're dealing with hardware failures and endless reset times and safety constraints too.
Right. So it's kind of like we are essentially trying to train a brilliant scholar who has read every physics book in the world, but has never actually used their hands to pick up a pencil.
That is a great way to put it, yeah.
And so latent action models, or LAMs, these are basically the current best fix for this missing physical data. Right?
Yeah, they are.
We are essentially making that scholar watch millions of hours of human and robot interactions on YouTube or whatever video, just so they intuitively learn how objects move and change states before they ever try to control a physical motor themselves.
Exactly. And the paper formalizes this into a very strict 3-stage pipeline, which is important to understand.
Right. Stage 1, Stage 2, Stage 3.
Yeah, so Stage 1 is pre-training on pure unlabeled video to learn these mathematical surrogates, which we call latent actions.
Okay.
Then Stage 2 is mid-training, where those latent actions are used to actually fine-tune the vision language model backbone.
Right.
And then finally, Stage 3 is post-training. That's where you introduce a very small, very expensive data set of actual physical actions to map those latent representations to real-world motor commands.
Which means the entire pipeline basically hinges on Stage 1.
It completely does. Because if your model cannot accurately extract a reliable, generalizable action from just watching 2 consecutive frames of a video, then the rest of the pipeline just collapses entirely.
Yeah, it falls apart.
Right. And the paper divides the field's current approaches into 2 main paradigms for modeling these latent actions. First, there's explicit modeling, also known as consecutive frame differences, autoencoding.
That's the CFD-AE, right?
Yeah, exactly. And this approach mathematically calculates the literal difference between frame A and frame B and encodes that delta directly.
Okay.
And then the second paradigm is implicit modeling. This is primarily the IDM, FDM framework, so that's inverse dynamics model and forward dynamics model.
Right.
The IDM tries to infer the latent action between 2 frames, and then the PM tries to predict the next frame using that inferred action.
I want to stop on the explicit models for a second because the benchmark results they got on Libero and RoboTwin 2.0, they present a pretty major kind of counterintuitive finding.
Oh yeah, the optical flow stuff.
Right, exactly. Because the researchers tested explicit optical flow models, specifically RFT and CRAFT, and optical flow literally tracks the movement of pixels from one frame to the next to right.
Yes.
So if a robot arm pushes a block, the pixels representing the arm and the block they move. So why would raw pixel movement perform so terribly while extracting semantic feature differences, like using delta DINO, meaning tracking how the abstract meaning of the scene changes? Why did that work incredibly well? I think Delta DINO even beat LAPO on the LIBERO benchmark, right?
It did, yeah. And the reason is that optical flow tracks motion completely indiscriminately.
Oh, okay.
So think about it. If the camera jitters by even a fraction of a millimeter, or say the ambient lighting shifts or a shadow moves across the background, optical flow registers that as a massive wave of pixel movement.
So it's just way too noisy.
Exactly. It encodes all of that noise as a quote-unquote action, and then the downstream model just wastes all its capacity trying to decode lighting changes into joint torques, which is useless.
Wow, yeah, that makes total sense.
Right, but Delta DINO, it operates in a pre-trained semantic space. DINO V2 already has a really deep representation of object permanence and affordances.
Right.
So when you calculate the delta in that high-dimensional semantic space, you automatically abstract away all that low-level pixel noise.
You just ignore it.
Yeah. You isolate the semantic state change, so like the drawer shifting from closed to open, and you completely ignore the camera shake.
Okay, that definitely explains why the semantic explicit trackers work so well. But, I mean, it kind of makes the performance of the implicit models even more surprising to me.
Yeah, it's pretty wild.
Because LAPO, which is a purely self-supervised implicit model, it learns from raw data without relying on a pre-trained semantic crutch like DINO V2, yet the paper shows the original LAO method remains this incredibly strong baseline champion basically across the board.
What's fascinating here is that LADO succeeds because its IDN-FDM loop enforces a really strict causal structure. By forcing the forward dynamics model to actually render the literal future frame based on the action inferred by the IDM, the network is basically forced to learn the underlying physics of the transition.
And it has to actually understand it.
Exactly. It has to understand spatial relationships and object dynamics just to minimize its reconstruction loss rather than just memorizing a static delta map.
Right, right. But the IDM-FDM loop, it actually has a critical structural flaw, right? Which leads us straight into the second dimension, the paper tests, which is regularization.
Yeah, the big one.
So LAPO suffers from a known issue called causal leakage.
Yep.
Basically because the inverse dynamics model takes both the current frame and the future frame as inputs during training to guess the action, it tends to learn an identity mapping. It's like giving a student an exam where the answer key is just printed on the back of the paper.
That is the perfect analogy, yeah.
The model just memorizes the future frame instead of learning the formula right, the transition dynamics.
Right, the OPM just acts like an information highway. It takes the visual features of the future frame and just passes them directly through the latent bottleneck to the FDM. It bypasses learning the transition entirely.
It's just cheating.
Complete cheating. It just memorizes the future state instead of learning the causal force that actually caused the transition.
So how do you fix that? Because obviously that's a huge problem.
Well, to prevent that identity mapping, you have to constrain the latent space. You have to restrict the information bottleneck so tightly that the model can no longer afford to copy-paste those high-dimensional visual features.
Right, it has to compress it.
Exactly, forcing it to compress the information into a pure abstract action. But the AI community has been highly fractured over the best way to do this. So the authors evaluated continuous regularizers like variational autoencoders or VAEs, sparsity penalties, and SIGREG. And they tested those against discrete methods like VQVAE, which forces the latent actions into a finite quantized codebook.
And the big reveal in this section is that the specific regularization method actually has a surprisingly limited impact on the final physical robot performance, right?
Very little impact, yeah.
Like whether you use VAE or sparsity or SIGREG, the downstream success rates on the benchmarks are almost identical.
It's pretty crazy.
Yeah. So what actually dictates success or failure is the hyperparameter strength, right? The lambda penalty.
Yes, the lambda penalty is absolutely everything here. Because if the penalty is too weak, the causal leakage just persists and the model goes back to cheating.
Right.
But if the penalty is too strong, you destroy the model's capacity to represent complex transition dynamics entirely. The latent space becomes overly smoothed or basically collapses, and the FDM just outputs blurry static frames.
It just breaks.
Exactly, it breaks. So the paper provides a highly specific set of golden rules for ML engineers who are listening to this. First, the latent dimensionality is critical. They found that a dimensionality of exactly 32 is the absolute sweet spot.
32. Okay, so what happens if you push that capacity higher, say, to 64 or 128 dimensions?
The model simply has too much bandwidth.
Yeah.
It reverts back to causal leakage because the bottleneck is wide enough to start sneaking those visual features through again.
Right, so it starts cheating again because you gave it too much room.
Exactly. And regarding the specific lambda values, The paper outlines exact starting points depending on your architecture. So if you're using a standard continuous space with a VAE, a penalty strength of 10 to the minus 7 is highly effective.
10 to the minus 7.
Yep. But if you are specifically building for out-of-distribution zero-shot generalization, and you prefer a discrete token space, use VQ-VAE with a penalty strength of 1.
Okay, wow, that's very specific. They also note that if your regularization strength is tuned correctly across that 32-dimensional bottleneck, you can completely skip latent action normalization, right?
Yeah, which is great.
Because normalizing the latent vectors, it adds unnecessary computational overhead, and it doesn't yield any statistically significant performance gains if the VAE is already bounding the space properly anyway.
Right, which simplifies the training pipeline significantly. You save compute.
Always a good thing.
Always. So basically, at the end of stage 2, we have a highly refined 32-dimensional latent action space that accurately captures the physics of state changes without leaking visual information.
Which brings us to the really hard part.
Yeah, the next challenge is plugging that abstract mathematical concept into a physical robot's brain to actually command its motors.
Right. Here's where it gets really interesting, because this is dimension 3, the integration strategies.
Right.
How do we actually wire the latent action into the physical action head? And the paper tests 3 specific architectures, DAP, LAP, and JJP. So DAP stands for direct action prediction. And in DAP, you use the latent actions during stage 2 to fine-tune the visual representations of your VLM. But then when you move to stage 3 to predict actual physical motor torques, you just throw the latent action away.
Yeah, you discard it.
You just map the fine-tuned VLM features directly to the physical action head, which seems kind of counterintuitive.
It is, and that's why DAP consistently performs the poorest among the 3, because it literally discards the structural logic of the action during inference.
Right.
It uses the video data to improve the model's visual understanding of the environment, sure, but it forces the model to learn the complex mapping from pixels to physical joint angles entirely from scratch.
Using only that tiny, expensive data set.
Exactly, using only the small data set of physical trajectories.
Yeah.
Which is just not enough data.
Right, okay. So then there's LAP, or latent action prediction, and this one forces the network to use the latent action as a mandatory intermediate step right. So the VLM predicts the 32-dimensional latent action, and then a downstream head takes that latent action and decodes it into physical motor commands.
And LAP is definitely better because it enforces the structure learned from those millions of video frames. But this raises an important question, right? Placing it as a strict bottleneck creates a brand new problem.
Because it's compressed.
Highly compressed. A come-to-dimensional vector captures the general semantic movement like move hand toward handle, but it inherently drops high-frequency, fine-grained visual details.
Oh, I see.
So when the physical action head has to decode precise millimeter-level spatial adjustments to successfully grasp that handle, it's completely starved of the necessary raw visual context.
Because it only sees the 32 numbers.
Right. It only sees that compressed latent vector. It's blind to the high-res details.
That sounds like a major structural limitation, and I guess that's exactly why joint action prediction, specifically a hybrid approach called JAP-LAP, takes the crown in this paper.
It is indeed.
Because in the JAP-LAP architecture, the network doesn't force the physical action to decode directly from the latent action right. Instead, it predicts both the latent action and the physical action in parallel, side by side, directly from the shared VLM feature maps.
Exactly. By predicting them jointly during the stage 3 optimization, the latent action head acts as an active continuous regularizer on the VLM backbone.
Oh, that's clever.
Yeah, it forces the shared feature maps to stay highly motion aware and structurally grounded in the physics that it learned from the video data.
Right.
But meanwhile, the physical action head still has direct access to the rich, uncompressed visual features from the VLM.
So it can still see the handle clearly.
Yes, allowing it to execute those millimeter-level spatial adjustments without being choked by the 32-dimensional bottleneck.
Okay, that makes total sense. But setting up this entire 3-stage pipeline, managing the IDM-FDM loop and tuning the VAE lambda to 10 to the minus 7, and then optimizing these parallel JIP-LAP heads, that requires a massive amount of compute.
Oh yeah, an unbelievable amount.
So engineers training these embodied foundation models, they need to know if their stage 1 model is actually learning useful representations before they go and burn thousands of GPU hours training stages 2 and 3, right?
Definitely.
They need a fast proxy metric. And the paper tests 4 specific proxies here: the linear probe, the MLP probe SSIM gain and MSE gain.
Right. So the probes are basically standard classification tests. A linear probe, or an MLP probe, takes the frozen latent representations from stage 1 and just trains a small separate neural network on top of it to see how well it can predict the ground truth physical actions.
Okay.
SSIM gain and MSE gain, on the other hand, are for dynamics model reconstruction metrics.
So they're testing the video side.
Right. SSIM stands for Structural Similarity Index Measure, and MSE is Mean Squared Error. Basically, they evaluate how accurately the latent action allows the FDM to render the literal next frame of the video.
But the data reveals a pretty major operational hazard here, right, regarding how engineers actually use these metrics.
Oh, yeah, it's a huge trap.
Because the authors found that all these proxies have a high Pearson correlation, meaning they generally track with downstream success. But they have a much lower Spearman rank correlation.
Right.
And so Spearman correlation measures how well the metric strictly ranks the models from best to worst. So if you have a cluster of highly competitive stage 1 models, the proxy metric is likely to just shuffle their absolute ranking entirely.
It absolutely does.
So if these proxy metrics can only give us a rough coarse grain screening with the Pearson correlation, but they completely fail at giving us a strict ranking of the best models, aren't we basically still flying blind at the finish line? Like if I just select the top scoring model on the MLP probe, I might actually be selecting the 3rd or 4th best model for my physical robot.
You're completely right. That is exactly what happens. The probe metrics are particularly unreliable because they are heavily influenced by the capacity of the decoder that you attach to them.
Oh, so it's testing the probe, not the model.
Yes, exactly. An MLP probe is essentially testing the linear separability and the capacity of the multi-layer perceptron itself to extract a signal, rather than the intrinsic physical grounding of the latent representation that you actually care about.
That's a great point.
So the paper strongly concludes that FDM reconstruction metrics, so the SSIM gain and MSE gain, they are far more robust indicators of actual downstream success.
Because rendering the future frame forces the model to prove it actually understands the mechanics of the scene.
Exactly. It tests true world modeling capability.
Right.
If the latent action is accurate, the FDM can properly occlude background objects, simulate object persistence, and basically translate pixels accurately. That aligns much closer with the causal reasoning a physical robot actually needs to navigate a real environment.
Yeah, that makes a lot of sense. But there's also a pretty severe warning in the paper regarding cross-dimensional evaluation rates.
Hey, you have to be so careful here. The authors strictly advise against using any of these proxy metrics to compare models that have different latent action dimensionalities.
Okay, why is that?
Because if you compare a 32-dimensional latent space to, say, a 128-dimensional latent space using an MLP probe, the 128-dimensional model will almost always score higher.
Just because it has more space.
Simply because it has a wider bandwidth to pass memorized visual features to the probe classifier, not because it learned better physics.
Oh, wow. So it's just cheating again.
Yes. It's an apples to oranges comparison that completely masks the causal linkage that's happening in the larger dimensional space.
Right. Okay. So you basically never use these proxy metrics to compare different sizes.
Never.
Got it. So all of these architectural findings and simulated benchmarks on Libero, they're incredibly detailed, but the ultimate reality check for any ML engineer listening to this deep dive is real-world physical scaling.
Oh, absolutely. Does it work on metal and plastic?
Exactly. Does a JJK-LAP architecture with a tightly regularized 32-dimensional latent space actually translate to hardware?
And to test this, the researchers executed a truly massive scaling experiment. They took their optimized architecture and they fine-tuned the VLM on 59 million frames of unlabeled video.
59 million?
Yeah, pulling from really diverse large-scale data sets like Deroid Language Table and Bridge. And the results basically confirmed that scaling video data directly translates to physical capability.
Which is what everyone was hoping for.
Right. On the LIBERO-Plus benchmark, which specifically tests for out-of-distribution environmental shifts and visual variations, the latent action-tuned model saw a massive 9% jump in success rate over the baseline.
9% is huge in this field.
It's massive, yeah.
And the actual physical deployment is where the metrics get genuinely impressive.
Right.
They deployed the model on a 7 degree of freedom Frankopanda robot arm, and it was equipped with a 1 degree of freedom UMI gripper.
Yep.
And they evaluated it across 4 distinct physical tasks. So there was closing a drawer, opening a drawer, stacking 2 bowls, and placing a block into a bowl.
Right.
And opening a drawer is notoriously difficult in these setups, right? Because The gripper is just bulky.
Very bulky.
The model has to precisely angle the gripper to grasp a really small round handle without just colliding with the cabinet overhang entirely.
Exactly. It requires a lot of precision. And the baseline VLM model, which was trained solely on the available physical action data, so no latent action video pre-training at all, it achieved a 64.75% overall success rate across those 4 tasks.
Okay.
But the latent action tuned model, leveraging those 59 million frames of video, it bumped that success rate up to 79.25%.
That's incredible.
But the most critical finding for ML engineers who are dealing with sparse physical data is the training efficiency.
Oh, right, the convergence rates. They're completely different, right?
Night and day.
So the baseline model required 40,000 training steps just to plateau at a 76% success rate on the open drawer task. But the LA-tuned model, it converged exponentially faster, right? It hit an 85% success rate in just 10,000 training steps.
Yeah, that is a 75% reduction in the optimization time required for the physical action head.
Wow.
And it's purely because the VLM backbone had already learned the universal mechanics of motion from all that video data.
Right.
The physical training data was no longer being used to teach the model how objects move. It was only being used to map an already robust physical understanding to the highly specific joint torques of the Frankopanda arm.
That is so cool. And the observation logs, they also highlight this really fascinating emergent behavior in the real-world testing.
The rogue bowl.
Yes, the rogue bowls. The LA-tuned model developed a super high level of robustness against visual distractors.
Yeah, this was amazing to rate.
Because during the open drawer task, the researchers actively tried to confuse the models by placing these task-irrelevant rogue bowls on the table just midway through the trajectory.
Right, just tossing them in.
And the baseline model just immediately suffers a distribution shift. It gets confused by the sudden appearance of the bowls, it switches its internal mode entirely, and attempts to basically interact with the bowls instead of the drawer handle.
It just completely loses the plot.
But the LA-tuned model just completely ignores the distractor bowls and successfully executes the drawer grasp, like it doesn't even see them.
Because the baseline model relies purely on its limited physical data set, its visual representations are incredibly brittle.
Right.
A sudden change in the pixel space just derails its physical action prediction entirely. But the LA-tuned model, having processed 59 million frames of diverse, noisy video data through that strict continuous regularizer, it has abstracted its understanding of the scene.
It knows what actually matters.
Exactly. It understands the causal sequence required to open the drawer, and it treats the sudden appearance of the bowls as just irrelevant background noise. Much like how Delta DINO abstracts away camera shake.
Right. So what does this all mean? I feel like this signals a massive shift in how we approach the entire data bottleneck. Latent actions are clearly no longer just some academic pre-training objective.
No, definitely not.
When they're tuned correctly, so using a JB-LAP integration strategy, bounding the capacity to 32 dimensions, and enforcing a VAE penalty of 10 to the -7, they are a highly proven engineering requirement for bridging the gap between simulation and real-world robotics.
It fundamentally changes the scaling laws for embodied AI. You honestly no longer need to scale human teleoperation linearly with the complexity of the tasks.
Which saves millions of dollars.
Oh, absolutely. If your foundation model can extract the underlying physics of the world from standard unlabeled RGB video, which we have plenty of, then the physical action dataset only needs to be barely large enough to calibrate the final motor mappings.
Which leads to a pretty incredible horizon for this technology, I think. Right now, this paper proves we can use latent actions as a highly efficient bridge rate to fine-tune existing VLMs. But what happens when we stop treating them as just an intermediate bridge or a hack and start treating them as foundational primitives?
Like text tokens.
Exactly. Think about text tokens in a large language model. What if we are looking at the immediate precursor to a true embodied foundation model, where action tokens are natively embedded into the architecture from day one?
Oh.
If a GPT-style model is trained from scratch on every single video on the internet, parsing the universal language of physics and motion as fluently as it parses syntax, a robot honestly wouldn't even need a teleoperated demonstration to understand how to use a tool. The very moment it connects to its cameras, it would already intuitively understand how every single object in its field of view interacts with the physical world.